And then, sorry about the noise. I think it's the room's heating. Share screen. Perfect. Oh, forgot to do one thing. Okay. And I guess we are good to go. Yeah. Okay. So basically, we have an assembly, slitter assembly that has 48 blades. And 5 blades are selected every day and tested, right? To see if the blade is dull. And then part A wants us to calculate if 10 blades are dull, what's the probability that the assembly is replaced in day 1, right? So the numbers that we have to remember is 48, 5, and 10, right? So we have basically 38 not dull blades and 10 dull blades. And we change the color. And we are selecting, I guess it was 5 blades, right? Was it 5? Yeah, 5 blades, right? So we are selecting 5 blades every day, right? And we want to see that whether in the first trial, right? So the first day that we test, do we find one of the 10 dull blades or not, right? So basically, we want to calculate the probability that at least one of the 5 selected blades is dull, right? So this is the probability that we want to calculate, right? And whenever you see at least, it's usually easier to calculate the complement, right? So we say instead of calculating, at least one of the 5 selected blades is dull, I'm going to calculate. So that is equal to 1 minus probability that none of 5 blades is dull, right? And now it's easy to do. So this is what we did in the previous class. 1 minus. So we want none of the 5 blades to be dull. So that means that I want all of the 5 to be among the 38 non-dull. And then my denominator is the total number of the ways I can select 5 blades. So that's 5 combinations of 5 from 48. And that's the final answer. So for the next part of the question, which is part B, it makes sense to call this something instead of this, long name P of this. So let's call this P of, replace, right? So I think the question said if, so the question said if a dull blade is selected, then the assembly will be replaced, right? So we call this probability of, being replaced, P of R, right? So any questions about part A? So let's move. So we already did part A. Let's move to part B. Now part B is asking if 10 blades are dull, what's the probability that the assembly is not replaced until day 3? Right? So it means that day 1st is not replaced, day 2nd is not replaced, and day 3 it is replaced. So for part B, so this is an interesting room. Every day there's a different type of noise in the room. I have no idea what's the source of these noises. Probably because of the construction in the lower level. So so basically we have 3 days. We want the first day to basically P of R prime. So we want the first day not to replace, second day not to replace, and then third day to replace, right? So this is the probability that we want. We want this and this and this. So there's an intersection, right? So now the question is, whenever you see intersection, we have to think whether they are independent or not, because if they are independent, it makes our life very easy. We just multiply individual probabilities, right? So this is what we discussed in the previous class, you know, so it looks like, you know, this company is making these slitter assemblies and is shipping them out, right? So these basically assemblies are independent every day, and also like we are checking different blades every day, right? So probability of not selecting a dull blade in the first day doesn't affect the next day. So here's what we have to like infer from the question, that these are independent probabilities. So basically the answer is going to be, so the final answer P of so here my notation is a little bit sloppy, because probability is a number, right? So we don't have intersection of probabilities, right? It's like saying intersection of 5 and 2, right? That doesn't have any meaning, right? So what I should have written instead was R prime, R prime, R, right? So this is what I should have written. And then I should have written up here that since these are independent, I'm going to multiply these by each other, right? So now my notation is correct. So the final answer, P of replaced in day 3 is going to be 1 minus P of R to the power 2 times P of R, right? And we have P of R from the previous part. That's why I denoted it with something short, so that I can write this short answer. Yeah. Oh, yeah, you can use negative. So this is a geometric distribution, clearly, right? So it's geometric because in the first day I have basically, if I go back, the question is saying that what's the probability that the assembly is not replaced until day 3? So it means that, let's say this is day, you know, n, right? So this means that it's not replaced in the n-1 days, and it is replaced in the nth day. So this is a geometric distribution. So I didn't use, sorry. So here I didn't actually use the geometric property. I just used the simpler rule of multiplication. Any other questions? So this was part B, and now let's try to do part C. I will go back. So part C is asking, repeat part B if the number of dull blades is as follows. So day 1, 2 blades are dull. Day 2, 6 blades are dull. And day 3, 10 blades are dull, right? So it seems like these blades are actually used every day, right? So because the number of dull blades is increasing per day, right? So I guess the first explanation that I gave on Wednesday is a better explanation why these events are independent, right? Because every day we check some blades, but we can check the same blade in the following day because that blade, you know, might become dull during the day. So basically what we have to do now, part C is as easy as part B or as difficult as part B. The only difference is that these probabilities change, right? So basically, I mean, that's the advantage of not using the geometric distribution, right? So here I didn't use the geometric distribution. And now, since the question is changing these probabilities per day, I can simply modify these, and solve part C. So I think it's often a better idea not to use these equations, and use the fundamental rule of multiplication and addition of probabilities, right? So in part C, again, the answer is the same thing. I want R prime, and R. So not replaced, and replaced. But the difference here is that I have to recalculate each one of these because the number of dull blades is changing, right? So in part C, I have to do the following: not replaced, but let's see how many dull blades I had. 2 for 2 dull. So this is day 1, and then day 2. Again, I have to do not replace, but here I have 6 dull blades. And then in day 3, I have replaced, but here I have 10 dull. Right? So I want the intersection of these events. And again, the events are independent, so I can simply calculate each one of them and multiply. Right? So so here we have 2 options. Either we can calculate, R prime, or calculate R and then subtract 1 from that. Either is fine. So what do you suggest? Should we calculate R prime or R?
Why are you saying R prime?
Yeah, R prime, because the assembly shouldn't be replaced in day 1. So the question is saying repeat part B. So that means that the assembly is not replaced in day 1 and not replaced.
Yeah.
So that's why we denote replace as R. So R prime, right? Sure, we can do that. So R prime, if we have 2 dull blades, is going to be, so basically what I have here is I had 48, right? So that means I have 46 not dull and 2 dull, right? And again, I'm selecting 5. And I want not replaced, right? So that means that I want these 5 that I'm selecting to be among the 46 divided by 5 among 48. So this is the first part. And then for the next part, let's write that with different colors. So here I want to calculate R prime. If I have 6 dull blades, so here I have 42 not dull and 6 dull. And again, I'm selecting 5. So this is going to be equal to, so what is the numerator? Exactly. 42, choose 5. And what's the denominator? 48, yes. What's your name? Muhammad? Yeah, that's correct. 48, choose 5. There you go. So that's the second part. How do we calculate the last part? Exactly, it's already there, right? So we don't need to recompute it. The third part, R of $10, was the first thing that we computed here. Right? So we have that one. So we have everything. All we have to do is we have to multiply this number by this number by this number. And that's the final answer. Any questions? Okay. So let's move on. So this was the exponential distribution that we discussed in the previous class. So we have 25 logins per hour, right? We did this part using both exponential and Poisson distribution, and it was okay. But for the next part, we tried to do it with the Poisson distribution, but it didn't work, right? So let's try to find out why that was, right? So this is the exponential distribution. This is 2 minutes. This is 3 minutes, right? So this curve here that I plotted is is 25 times e to the minus 25x. This curve is x, and sorry, this axis is x, and this axis is f of x, right? Probability, PDF. So in this part, using exponential, we calculated this area under the curve, right? Between 2 and 3 minutes. And the answer was this number. So this area under the curve is 0.152, right? So in the previous class, we tried to solve this using the Poisson distribution. So what we did is the following. So we said, okay, between 2 and 3 minutes, that's 1 minute, right? So first I have to convert my 25 login per hour to logins per minute. So my lambda for Poisson distribution is going to be 25 logins per 60 minutes, right? So this is the unit of this is number of logins by minute, right? And then I said, okay, I want there to be, some login here in this 1 minute interval, right? So what I'm going to say is that the probability of some login here is 1 minus probability of no login, right? So I said, what I'm interested in is probability of, at least 1 login in 1 minute, right? So that is going to be 1 minus probability of no login. So 1 minus probability of no login. And that is going to be 1 minus e to the minus lambda to the power x divided by x factorial. Can anybody verify that this is the distribution of the Poisson? I think this is correct, right? Yeah, this is the Poisson. Thank you.
It's correct, yeah.
Thank you. So here I have to plug in no login, means that my x is 0, right? So this means that my x is 0. So I plug in x equal to 0. So that's going to be 1 minus e to the minus 25 divided by 60, and then times lambda to the power 0 divided by 0 factorial, and that's 1 minus e to the minus 25 divided by 60, right? And the answer that we calculated was exactly 2 times the previous answer. So it was, so what is 2 times that? 0.34, I guess. Did you verify? Okay, thank you. That's fine, yeah, just 2 decimal points is okay. So I usually ask this from you guys, but since this is beyond the scope of this course, I explained why the two numbers are not the same, right? So what we calculated in the second part was probability of no logging in 1 minute, right? So here they basically the origin is from 0, right? So basically what we calculated is this other area from 0 to 1 minute. It's this area that we calculated. Not the area that the question wants, right? So we calculated the probability that, you know, no logging happens in 1 minute, but 1 minute starts from when? Starts from right now, right? So that was our mistake. We didn't actually solve what the question wanted. We solved something else. And the number just happened to be 2 times that. That's why we couldn't, you know, we couldn't find out why it's incorrect. It's just a coincidence. It's 2 times more. So this is the area. So if you actually, it's a very good suggestion that I have for you guys. If to calculate this area, here plug in 0 and here plug in 1 minute. So 1 minute will be 1 divided by 60, right? And you will see that the answer you will get is exactly this number. So we actually calculated some other probability. So you see that it's I told you guys about, you know, this connection because it's important to know, but you have to be very careful. If the question wants, you know, to calculate some probability in some time interval, it's just safer to use exponential, right? Because we made a mistake in the class trying to use Poisson. Right? So just use if the question is asking, you know, some probability in some time interval, just use the exponential distribution. If the question is asking the number of what's the probability of having this many, you know, like incidents, then use Poisson distribution. So look at the question, see what is the random variable, and use exponential if it's continuous, or Poisson if it's discrete. Yeah.
If we consider x as time, will lambda change?
Here?
Yeah.
Oh, here x is not. It's a very good question. So in the second part, we cannot consider x as time. X is the number of events. Okay. So it's not allowed to consider x as the, you know, time between the incidents if you are looking at the Poisson distribution, right? So here my x is a completely different x as here. So here my x is time, and here my x is something completely different. Here my x is number of logins. So 2 different x's. So you are not allowed to assume your x is time here. It's not allowed.
Sir?
Yeah.
Isn't the Poisson distribution memoryless? So the probability of having an event in the next minute, regardless of when this minute is.
Yeah, so that's an excellent question. So the question is, it's memoryless, right? So, but that's a completely different concept, right? So here, looking at the curve, right, we see that the time, the probability between 0 to 1 minute is obviously more than the probability between 1 and 2 minutes, is obviously more than the probability between 2 and 3 minutes, and so forth, right? So this fact, the fact that these probabilities change, has nothing to do with the memoryless property, right? It's clear from the curve that the curve is exponential curve, so it's always decaying. So as you go further and further, probability gets less, right? The memoryless property was something completely different. So the memoryless property, so if I enter, let me see if I have some white space here. Yeah, there you go. So if I have an exponential curve like this, so this is, you know, time t, this is time 2t, this is time 3t, this is time 4t, and so forth, right? So probability that my x is between 0 and t is more than the probability that my x is between t and 2t, and that is more than the probability that my x is between 2t and 3t and so forth, right? And we can see that clearly from the curve. This is more than this is more than this, and so forth, right? So the probabilities do decrease. And that is not anything to do with the memoryless property. This is not conditional probabilities. We are looking at the memoryless property only applies if we are looking at conditional probabilities, right? So that's a different thing.
Oh, given that nothing happened, no X happened before. Okay.
Exactly. Yeah. So look at here. P of X between 2t and 3t is less than P of X between 0 and t. But if we want to relate this to the conditional probability, then we can say that P of X between 2t and 3t, oops, sorry, given that X is already more than 2t, then this is equal to P of X between 0 and t. So if we
got it. Thank you.
Yeah, if we condition it, then they are equal. But in the previous question, we weren't looking at conditional probabilities. So don't worry if this seems, I think this is borderline in the scope of this course because we are just looking at conditional probabilities, right? But it's probably a little bit beyond the scope of this course. So don't worry if, this doesn't make sense to you. Any questions? Okay, so let's move on. So see what time is it? How many people want me to solve this one? So if it's okay, if you find these questions difficult, it's completely fine. We haven't done, yeah, sure. Let's do this one. So we want to calculate the probability that the following circuit operates, right? So the question says the circuit operates if there's a path of functional devices from left to right? So if there's operation from here to here, then this circuit operates. The probability of failure of each device is shown. So in this question, it is very important to remember that this is probability of failure, right? Each piece works independently. So that means that we can simply multiply intersections. What's the probability that the circuit operates, right? So I always encourage you to make these questions, break a large question into several smaller questions, right? So what we are going to do is that first we are going to calculate the probability of the left part operating, and then calculate the probability of the right part operating, and at the end multiply the two by each other, right? So basically, okay, so I'm going to call this probability that left part. So I also should be careful what I call this. So I can either call it left part operate or left part fails, right? Any suggestions? Yeah.
It's either up and down.
Yeah, we could do that. Yeah. So I mean, we could break further into, let's just break it into two first, and then we break we break each one into another two. So we can either calculate P of left part failing or P of left part operating, right? Either one is fine, but we have to remember what we are calculating. That's very important. So let's calculate probability of left part, operating, right? And again, we call the probability of this part operating P of right part operating, right? And then my final answer is going to be, what's the probability that the circuit operates? So probability that operates is going to be P of left part operates times probability of right part operates, right? Because both of them have to operate for this circuit to operate, right? So now I broke the problem into two smaller problems. All I need to do is to calculate this and this, right? So first, let's calculate the probability that the left part operates, right? So let's just remember these numbers, 1%, 1%, and 10%. So this is the left part, 0.01, and then another 0.01, and then 0.1. So again, very important to remember that we are interested in calculating the probability that this thing operates, but here I've written the numbers that it fails, right? So if you remember in the class, once we did one of these and I did make this mistake, right? So let's try to calculate this. So probability that left part operates. Okay, so for this to operate, either one of these two have to operate, right? So now I can do this. So I can look at this. I can call this, you know, so I can call this bottom part, left bottom part. So again, I have to decide between operate and fail, right? So what is the probability that the left part operates? Either one of these two have to operate, right? So perhaps it's better to calculate probability of failure and then subtract one, right? Because it's either one of them. So this is going to be probability that left bottom part, and this, I call this one left top part, right? So this is going to be 1 minus probability that both the top part and the bottom part fail. So left bottom part fail, and then probability that the left top part fail, right? So probability that the left part, that this thing operates, is going to be 1 minus probability that both of these fail, right? That's the only case that this thing can, you know, operate. So if both of these fail, then this fails. So 1 minus that is the probability that I want, right? And now we are good to go because all of these are easy numbers to write down. So 1 minus probability of the left bottom part failing. So left bottom part failing is already given. It's 0.1, right? And then left top part failing. For the left top part to fail, either one of those two guys has to fail, right? So so probability of left top part, probability of left top part failing. I'm too close to the border, so I get. Is equal to, so left top part failing is going to be, so either one of those two guys has to fail, right? So what's the probability that either one of those fail? It's going to be 1 minus the probability that both of them operate, right? So 1 minus, so the first guy operating is 0.99, and then the second guy operating is also 0.99. Right. So let me, before you ask question, I'm not sure if what I wrote is correct. So let's check. So probability of this thing failing, for this thing to fail, either this has to fail or this has to fail, right? So whenever I say either or, it's possible to calculate the probability of complement, right? So I'm saying probability of this thing failing is equal to 1 minus probability of this thing operating, right? So what's the probability of the top part operating? The top part operates if both of these operate, right? So the probability of this operating is 0.99, probability of this operating is also 0.99. So what I wrote is correct. So I will explain again. Probability of this thing failing is equal to 1 minus probability of this thing operating. So what's the probability of this operating? This has to operate and this has to operate. So that's my answer. This is not the only way, right? There are many, many ways to find this. Yeah, go ahead.
Could it be additive?
Yeah, you can add, exactly. So you can add, that's fine. Yeah. Yeah.
So the question says that if one of them fails, then the system doesn't work.
No, not if one of them, no, that's not correct. So here, for example, this thing can fail but the circuit can operate because the other path works. So it's not that if one of these fails, the system fails. No, there has to be a path. Oh, one of the top ones. You're right. Yeah, if one of the top one fails, then if one of these guys fails, then the top path fails.
So then we have three options. We have both of the top failing, one of the top failing, the second one.
Yeah.
One of the passing.
Yeah.
And then we just add all three.
And then subtract the union intersection, right? So this was one way to write. So let's do that one, right? So it seems like the top part is a bit confusing. So let's write the probability. So I wrote down one way to calculate probability of left top part failing. So this is left top, right? So this is one solution. We can calculate this using another technique. So I can say that probability that the left top part failing is also equal to either this fails or this fails, right? But whenever we do that, we have to subtract the probability of the intersection because we counted the intersection twice, right? So this is, there's a 0.01 chance that this guy fails, right? There's also a 0.01 chance that this guy fails, but there is some chance that both of them fail, right? And when we simply add, we have to subtract the case that both of them, because we counted this guy twice, right? So here, left top part fail is going to be probability that this thing fails, which is 1%, plus probability that the other one fails, which is again 1%, minus probability that both of them fail, and that is 0.0001, right? So here I use this property that P of A union B. So either this fail or the other fails is equal to P of A plus P of B minus P of A intersection B. So in this case, the number that we subtract is very small because these probabilities are small, right? But that's not always the case. If these guys had a larger probability of failure, then this would be a considerable number, right? So that's why I wrote it like this, because I think this is easier than this. This has 2 terms, this has 3 terms to add. So anyways, let's write the final answer. So either this or this, right? So 1 minus 0.99 to the power 2. So we calculated the left part. Probability that the left part operate is this guy. Oh, so intersection here means that A fails, and so what is A? A is, so let's call these guys some names, so let's call this, let's call this resistor 1, and let's call this resistor 2, right? So A here is resistor 1 failing, and B here is resistor 2 failing. And the intersection is both R1 and R2 failing, right? So remember, whenever we say, oh, either this guy fails or this guy fails, and we add them up, we always have to subtract the probability that both of them fail because we counted that thing twice. That's the intersection. Yep. So the top, you mean this guy? Or this one? Yeah, so the top part, I said that this basically branch at the top fails. The probability of this branch failing is 1 minus the probability of this branch operating. right? So what is the probability that this branch operates? The probability that this branch operates is basically this branch only operates if both of these guys operate, right? So what's the probability that both of these operate? 0.99 times 0.99. So 0.99 to the power 2. So in fact, we calculated difficult parts, right? So we calculated the left top part. Now let's go back, see what was the left, what was the right part. So the right part is 0.1 and 0.1. So let's draw it again. So 0.1. Oops. And then another 0.1. So here I want to calculate the probability that this thing operates, right? So probability that right part operates is going to be, so for this to operate, there has to be at least one path from left to right, right? So again, I can solve this using many different ways. So I can say that I can denote A. So here my A, my set A is the top path working. And my B here is the bottom path working, right? So probability of the right part work is equal to either the top part has to work or the bottom part has to work. So this is equal to probability of A union B, and that is probability of A plus probability of B minus probability of intersection, right? And that is equal to P of A is probability of the top part working is 0.9. Probability of the bottom part working is again 0.9. Probability that both of them work is 0.9 to the power 2. So can somebody plug this in into a calculator, punch it to see what's the answer? 0.99. Thank you. Exactly, that's also correct, and it gives you the same answer. Left, oh, left part, you mean this part? Yeah. Yeah. So probability of this thing failing is, these are the probabilities of failure, right? So the numbers written here, 0.1 is probability of this component failing. So I wanted the probability of this component failing, and that is 0.1. Right? Left bottom failing and left bottom failing is 0.1. And the other question was, can we calculate this using another approach, you know, right part operating? And the answer is yes, we can do this using another approach. There's no room here to write down the other approach, but basically I try to write very small. So again, this thing, probability of right part operating is equal to probability 1 minus probability of right part failing, right? and that is equal to, so when does this thing fail? It fails only if both of these guys fail, right? So that is going to be equal to 1 minus, so what's the probability of the top part failing? 0.1. So this thing fails if both of these fail. So probability of top part failing and bottom part failing is 1 minus 0.1 to the power 2. And this is again 0.99. Exactly the same answer as this guy. So as you see, there's many ways to solve these problems, many ways. And the best recommendation is always be clear what you're calculating, probability of operating or probability of failing, because it's very easy to confuse them. Any other questions? Let's move on. Okay, so let's basically try to draw the tree diagram for the following two questions. In part, so we have basically a bucket with 9 stars and 11 cubes. In part A, we pick 2 items with replacements, right? So the tree diagram is very good in helping you visualize different outcomes. So this is the first item that we draw. So the first item can be either a star, or the first item can be a cube, right? And the probability that the first item is a cube is 11 divided by 20. And the probability that the first one is a star is 9 divided by 20, right? So this is my node. And then so now I'm going to draw the second branch with a different color. So here again, the second item star, or the second item cube, right? Yeah, so if it's with replacement, so first I'm solving part A. Yeah, so if it's with replacement, then it's again the same numbers as before, right? So 9 divided by 20 and 11 divided by 20, right? And so forth with the other branch. I'm not going to write the other one. But the numbers basically, the take-home message is that if it's with replacement, these numbers, repeat themselves. So this is 11 divided by 20. This is also 11 divided by 20. Because probabilities don't change. Right? But in part B, the story is different. Again, I'm at the node. So first item star, and then first item cube. So this is 11 divided by 20, and this is 9 divided by 20, right? But here the probabilities change. So for second item star, since I already picked one star, this is going to be 8 divided by 19, and this guy is going to be 9. So second cube, and this probability is going to be 11 divided by 19, right? So we see that these numbers actually change now. So this is 11 divided by 19, and this was 11 divided by 20, right? Any questions? Okay, so let's move on. So I think this was also in some midterm exam, this question. So historic data shows that in Montreal in June, there are around 12 cloudy days and 18 sunny days. Assume that the weather in each day is independent from its previous day. What's the probability that June 1st is sunny? Exactly, 18/30. And then in the second part, the question is, what's the probability that 18 days are sunny in June of this year, right? So I guess this was like a midterm exam in 2017. So the question was 2017. So what distribution should we use? Louder? Exactly, binomial. So it's basically 18, choose 30 times. So we have to be careful what we are writing as probability. So 18 days are sunny, right? So 18 divided by 30 to the power 18, and then 12 divided by 30 to the power 12. So that's the answer, which is 0.147. Any questions? Okay, so let's move on. So this is the midterm just a few months ago. Potholes damaged the suspension of cars, and the cities try to maintain a low number of potholes to avoid extensive damage to cars. Each kilometer of roads must have less than 4 potholes, right? So each kilometer should have less than 4 potholes to avoid damage. Assume that the number of potholes follows the Poisson distribution. Engineers in the city have determined that by the end of winter, the average number of potholes in each meter is this number. In each meter, number of decimal point is needed. Okay, so find the probability that the city's road do not cause extensive damage to the cars, right? So the question says, to avoid extensive damage, the number of potholes must be less than 4. So basically, we want to calculate probability that 0 pothole, right? So here, PH stands for pothole, not for penthouse, plus probability of 1 pothole, plus probability of 2 pothole, plus probability of 3 pothole, right? And the question says each kilometer, right? So we better convert this lambda to kilometers. So my lambda is this times 1000. So that's going to be 2 potholes per kilometer, right? So the rest is super easy. I just have to plug into the exponent to the Poisson distribution. So this is going to be equal to, this is my lambda. So that's going to be equal to e to the minus lambda to the power x divided by x factorial. This thing, x is from 0 to 3. So that's it. Yeah. How many cars? This is not about the car, right? So do not cause extensive damage to the cars. So in order not to cause extensive damage, the number of potholes has to be 0, 1, 2, or 3. Okay, so that's it. That's the final answer. I'm not going to write down it. In the next slide, there is actually the numerical answer to this. Any questions about part A? So the rest is super easy. We just have to plug in lambda is equal to 2 and x is from 0 to 3, right? So it's just plug into the equation. So next part, assuming that the driving along a 1 kilometer stretch of road has caused no damage, what's the probability that the stretch has no potholes, right? So this is obviously a conditional probability. So the question is saying, what's the probability that the stretch has no potholes? No pothole. Given that has caused no damage. So given no damage. Right? So this is what the question wants. Right? So in my opinion, this is the most important part of solving a question. When you read the English, you should be able to convert it into the conditional probability language. So we want to calculate probability of no pothole, given that there was no damage to a car, no extensive damage. So again, reading the question, probability of no pothole is basically 0 pothole, right? Oops. Given no damage to the car, the question says that the number of potholes must be less than 4. So that means that I have either 0, 2, 3 potholes. So I have to calculate the probability that I have 0 potholes, given that I already know that the number of my potholes is from 0 to 3, right? Because if there was no damage, it means that I can't have 4 potholes or 5 potholes. Right? So now I use the definition of conditional probability. That's going to be probability of the intersection of these two. So what is the intersection of these two? What's intersection of 0 pothole and 0 to 3 pothole?
Just
0 pothole.
the probability of 0.
Yeah, 0 pothole, exactly. So that's going to be 0 pothole. And then the probability of 3 to 3 pothole, right? And by the way, what we calculated up here was the probability of 0 to 3 pothole, right? So we are in business, that's it. We just simply plug in. So probability of 0 pothole is going to be e to the power minus lambda times lambda to the power 0 divided by 0 factorial, which is 1. I'm not going to write that. And then the numerator is known from the previous part, probability of 0 to 3 pothole. So that's it. That's the final answer. And this is also, by the way, 1. Yeah.
If the question was assuming that driving along was 2 kilometers stretch of road, then lambda would change.
Yeah, exactly. You have to recompute the lambda. Any questions? So let's move to the next question. So do calculate the final answer and make sure that the number that you get is similar to this number. Okay. So automatic classification of an email as spam from its content is not easy. Assuming that from historic data, we know that the phrase get rich fast is present in 15% of spams. And only 0.1% of valid emails. Historic data also tells us that 30% of emails are spam. Finally, so historic data tells us that the phrase Nigerian prince is present in 10% of spam emails. So I know actually people who have fallen for this, not for the Nigerian prince, but for similar tricks, right? 10% of spam emails. In fact, recently I got an email and the sender was the wife of Jeff Bezos, Mackenzie. So she was saying that I have $1 billion that I want to donate. Mackenzie Scott, I guess. So yeah, it's not always Nigerian prince. It changes with the with the news. 10% of emails and only 0.1%, 0.5% of valid emails. Denote spam as S, valid as V, get rich fast as G, and Nigerian prince as N, right? An engineer receives an email that contains the phrase Nigerian prince, right? So probability, we have to calculate the probability of something given that the phrase Nigerian prince was in it, right? So N, right? So the question says an engineer receives an email that contains the phrase Nigerian prince. So we quickly condition on N. What's the probability that is actually from a Nigerian prince and it's not a spam? So we want to calculate the probability of S prime. The question says not a spam. So should we read it as S prime? Or actually the question says valid as V. So, I mean, we could denote it as S prime, but since the question says denoted as V, let's just write V. So that's the probability that we want. Probability of valid given N, right? So this is the question. So let's reread the question to basically write down these probabilities in terms of conditional probabilities. So the question says the phrase get rich fast is present in 15% of spam emails. So that means that probability of, so what was get rich fast? So get rich fast is G here. So probability of G, given that we are looking at the spam, is 15%. And also probability of G, given that actually given S prime. Or the question says S prime is V, is 0.1%, right? So probability of get rich fast in spam emails is 15%, and in valid emails is 0.1% from here. And then continuing, historic data also tells us that 30% of emails are spam. So this means that probability of spam is 30%. And then historic data that tells us that the phrase Nigerian prince is present is 10% of spams. Given spam is 10%. And only in 0.5% of valid emails. So probability of Nigerian prince in valid email is 0.5%. So that's it. The question is almost solved, right? So basically the main challenge here is to convert an English sentence into mathematical notation, right? After that, it's done. So first, let's see actually if we have this. So probability of V given N. So the closest thing we have is the opposite, probability of N given V, right? So whenever we have the opposite, like the order is reversed, we have to use the Bayes theorem, right? So we simply write down that probability of V given N is equal to probability of N given V times probability of V divided by probability of N. And the rest is easy. You just have to plug in the numbers. The only difficulty here is always the denominator is a bit tricky to calculate. So basically here we have to calculate P of N, and that is equal to P of, so remember, probably here. So these are all the emails that have the phrase Nigerian prince N. Some of them are valid email and some of them are spam emails, right? So this is the set of all emails, right? Some emails are spam, some emails are valid, and Nigerian prince is present in both valid and spam emails, right? So from this Venn diagram, we see that probability of N is equal to probability of N in spams times probability of spams plus probability of N in valid emails times probability of valid emails, right? So this is from the Venn diagram. And now we have all of these probabilities, right? What's the probability of? So probability of V is 1 minus this. So probability of spam is 30%. Therefore, probability of V is 70%. Yep.
So you're going to solve the question, quiz question.
So yeah, so there's unfortunately no time to solve the quiz question. If the quiz question doesn't make sense to you, then we have a POD on Tuesday, right? So you can ask the POD on Tuesday about the, I was going to, but it's already 11:30. Any questions about this question? So you can also come and we can solve it after the class, right? Because I don't want to stop everybody just for that question. So perhaps it's easier if you just come by right now and we solve the quiz question together. So good luck in the midterm exam on Wednesday. Make sure you arrive on time because we start and it's only 45 minutes. So if you arrive 15 minutes late, then you lose, you know, a good percentage of your time. Yeah. It's 4 questions. So is there questions from the audience in over Zoom? Is it still recording? Oh, yeah.